questions 21 through 25 on the 2020 Grade 10 AMC 10A. There exists a unique, strictly increasing sequence of non-negative integers a1 less than a2, so on until ak, such that 2 to the power of 289 plus 1 over 2 to the power of 17 plus 1 is equal to 2 to the power of a1 plus 2 to the power of a2, all the way until 2 to the power of ak. What is k? Well, the first thing I hope you can notice is a relationship between those two numbers, and that 17 squared is actually equal to 289. So what we can do is we can let 2 to the power of 17 be some variable. We'll just call it x. And that means that 2 to the power of 17 to the power of 17 is 2 to the power of 289. So that really is just x to the power of 217 is 2 to the power of 289. So our equation here we can rewrite in the following way. We will have 2, let's see here, x to the power of 17 plus 1 over x plus 1, and that is equal to all the stuff here. And we have to sort of figure this out of how many numbers we're going to have, a1, a2, all the way until ak. So how many of those? Okay, so some of you are very familiar with this kind of division. You can do it, but I'll talk you through it. So let's say we have something here, right? Some big long expression. Well, the first term, when I multiply it by this guy, if I cross multiply it, it's going to multiply by that x, and it's going to give me x to the power of 17. So that must be, therefore, x to the power of 16. And then the next term that I multiply is going to be this 1 times x, 1 times that x to the power of 16. So that's going to give me a plus x to the power of 16. But we obviously don't want that, because on this side there is no such x to the power of 16. So what we can do is we can put a negative x to the power of 15. So when this is multiplied by that, it will become x to the power of 16, and then it will cancel out what happens when you multiply that by that. So I hope that makes sense. And then if you keep going like that with the same sort of reasoning, when you multiply this by this, it'll be negative x to the power of 15, but we don't want that because that's not in that numerator. So we can add an x to the power of 14, because when you multiply this by this, you'll get an x to the power of 15, and it will cancel out that x to the power of 15, that negative x to the power of 15. And then you just keep going like that. So this will be minus x to the power of 13 plus x to the power of 12, and so on, all the way down to the very last term, which will be plus 1. And if you are not convinced of that, I encourage you to maybe make a smaller example. You know, this goes all the way to 17. Make a smaller one, maybe x to the 5, and then do this process and then multiply it out, cross multiply, and see if the left side is indeed equal to the right side. Okay, so now I'm going to factor. There's some obvious factorization here, x minus 1. If I factor out the x to the power of 15. Here, if I factor out an x to the power of 13, I will get x minus 1, and then so on, like that, dot, dot, dot. And then at the very end, you will get an x, and then x to the power of 1 times x minus 1. And then there's going to be this lone plus 1 out at the very end. Don't forget about that. So now we can factor out an x minus 1 from everything, and it will be x to the power of 15 plus x to the power of 13 plus dot, 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 all the way until that x to the power of 1. And then don't forget that plus 1. Okay. Now, let's see here. What do we do at this point? Well, now I think we are ready for that substitution. And that substitution was what we did at the very beginning, that x was 2 to the power of 17. So we got 2 to the power of 17 minus 1. And then when we put x as 2 to the power of 17, this will become 2 to the power of 255. This will become 2 to the power of 221. and then so on. You're going to have it all the way down to 2 to the power of 17 plus 1. Okay. Now we are ready to talk about this next step. This right here, that I just want you to figure out how many terms are there. And that's not hard. This was basically 15, 13, 11, 9, 7, 5, 3, 1. So that's 8 terms. So put that there, 8 terms. Now I want to figure out how many terms is that. Well, right now it's not really very obvious because I want to know how many of these powers of 2. Well, I'm going to have to probably put it in a different format to figure that out. Because right now it's a negative and I don't like that. I've got to have it in a positive. I've got to have all positive terms. So to avoid confusion, I'll do it on the side here. 2 to the power of 17 minus 1. And I want it to be sum. I want it to be plus, plus, plus like that. Okay, well, that, let's say, is n. So that means 2 to the power of 17 is equal to n plus 1, right? Now, I still don't know what n is. Well, if we make, say, n equal to a string of powers of 2, then that will help. Can I do that, though? Well, let's see. I have to add another 1 here because powers of 2, if I'm going to start with 2, I have to have at least another 1. So that's going to give me 2. And then if I add a 2, that gives me 4. That's 2 to the power of 2. If I add a 4, that now gives me 8, which is 2 to the power of 3. If I add an 8, that now gives me 16, which is 2 to the power of 4. If I add a 16, now that gives me 32, is 2 to the power of 5. And I keep doing that until I get to essentially 2 to the power of 16. And all of these, when you add them all up, equal 2 to the power of 17. So if you want to write it out as powers of 2, maybe it'll be a little bit more easier to understand. So this is 2 to the power of 2. This is 2 to the power of 3. This is 2 to the power of 4. This sum is 4, which is 2 to the power of 2. This sum is 8, which is 2 to the power of 3. This sum is 16, which is 2 to the power of 4. This sum is 32, which is 2 to the power of 5. And with that, this whole sum, whatever that number is, will be 2 to the power of 17. So I hope you get that. All right, let's go back and substitute this in. So that 2 to the power of 17 minus 1 is really just this whole string right here, which would basically be, I have to subtract 1 here because this is 2 to the power of 17. So it would be just this right here without that 1. So it would be 1 plus 2 plus 2 to the power of 2 dot 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 all the way until 2 to the power of 16. And then this one is our 8 terms as described above. So now how many terms are there? Well, let's count them. This is 2 to the power of 1 all the way to 2 to the power of 16. That's 16 terms. And then there's this one also. So there's 17 terms. Okay, so that means when I take these 17 terms and I multiply by these 8 terms, that's going to give me 17 times 8, which is 136 terms. And then don't forget there's one extra term here. So I have a total of 137 terms. And each of those will be some power of 2. This one, for example, is 2 to the power of 0. And then there'll be a whole bunch of other powers of 2. And there will probably be in increasing order. But what we are interested in is how many. So there's 137 of them. So the very last one will be A137, 2 to the power of A137, like that. So that is pretty much what they wanted, and 137, therefore, is C for number 21. For how many positive integers n less than or equal to 1,000 is 99 over n plus 99 over n plus 1,000 over n, 998, 999, 1,000, all over n, bracket, and not divisible by 3. Recall that x bracket is the greatest integer less than or equal to x. Well, I want to first talk about what is 99 in terms of its prime factors. It is 3 to the power of 3 times 37 to the power of 1. And therefore, there's 3 plus 1, and then 1 plus 1, number of divisors. So 4 times 2, 8 divisors for 999. In a very similar way, what about 1,000? 1,000 in its prime factorization is 2 to the power of 3 times 5 to the power of 3. So the number of divisors would be 3 plus 1 times 3 plus 1, which is 4 times 4, which is 16. So we have 16 divisors there. Okay, so if n is a divisor of 999, then let's see what happens. This 999 over n bracket, it basically becomes 1 plus 998 over n bracket. So, for example, if you're not convinced, let's say n is 9. You can choose any. Then we'd have 999 over n, which is 9. And on this side, you'd have 1 plus 998 over n. This side just becomes 111. This becomes 110. And that you have to add that 1. So indeed, the left side equals right side. Now, in addition to this, 999 over n, if n is a divisor of 999, would be equal to 1,000 over n. And I encourage you to use any example to sort of show yourself that. So if I let this guy 99 over n equal, say, some a, this is equal to a, then this sum up here would basically be a minus 1 plus a plus a. And that is 3a minus 1, which is not divisible by 3. Any number of the form 3a minus 1 would be not divisible by 3. So we want basically this as one of our scenarios, that n is a divisor of n. Because if it is, that sum would become 3a minus 1 as shown above. All right. So that is the first part. The second part is very similar, and that's if n is a divisor of 1,000. If that is the case, then we have 1,000 over n, the bracket. That would be equal to 1 plus 999 over n. And as I said, you can use any divisor of n to sort of prove this to yourself. And then similarly, 1,000 over n would be equal to 1 plus 998 over n. So, as before, if I let this guy equal, say, b, whatever you want, then our equation up here would become b, and then 999 over n would basically be b minus 1, and this one would be also b minus 1. So when you add this, it would be 3b minus 2. And that is also not divisible by 3. 3b minus 2. No number of this form would ever be divisible by 3. So we want n to be a divisor of 999, or we want n to be a divisor of 1,000. But not both. That's an important point, but not both. because if it's a divisor of both 999 and 1000, for example, the only such number I think is 1, because these don't have any common prime factors. Yeah, so the only number that's common is 1. If it's 1, then if you substitute n equals 1 into here, you'll notice that this sum will be divisible by 3. Okay, not a problem. So the total number are 16 and 8, because we want n to be a divisor of 999, or we want n to be a divisor of 1000. So there's 16 of those, 8 of those, so 24. But we cannot have 1, as the n cannot be equal to 1, basically. N cannot be equal to 1, as I previously mentioned. And 1 is going to be in this list, and 1 is also in this list, so we have to subtract 1 twice. So from that, you have to subtract, sorry, that was 16 plus 8, this 16, this 8. And from that, you have to subtract 2, because you have to subtract 1 from this list and 1 from that list. So that gives me 24 minus 2, which is 22. So number 22, the answer is 22, and that is choice A. Let T be the triangle in the coordinate plane with vertices 0, 0, 4, 0, and 0, 3. Consider the following 5 isometries, rigid transformations of the plane, rotations of 90, 180, or 270. Counterclockwise around the origin, reflection across the x-axis, and reflection across the y-axis. How many of the 125 sequences of 3 of these transformations, not necessarily distinct, will return T to its original position? For example, a 180-degree rotation followed by a reflection across the x-axis, followed by a reflection across the y-axis, will return T to its original position, but not a 90-degree followed by a reflection across the x-axis and another reflection across the x-axis. It will not return T to its original position. All right. Well, we have quite a long question, but hopefully I can explain it. So we've got this very interesting sort of set of transformations, reflections, whatever. So here's our triangle. We got 4 here and 3 here. Now, we have 3 moves, right? 1, 2, 3. And for each move, we have 5 choices. So 5, 5, 5, and therefore we multiply and we get 125. And that's exactly what they told me in the question, 125 sequences. But of these 125, only some of them would bring T back to its original position. That's why the answer choices are so much less than 125. Okay, this is one of those rare gems where part of the answer is given to you in the question. For example, a 180-degree rotation followed by a reflection across the x-axis followed by a reflection in the y-axis will return T to its original position. Okay, so I'm just going to call these 90, 180, 270, x-axis, y-axis, those moves. So the question already tells me that a 180 followed by an x-axis followed by a y-axis is one of the answers. Okay? You think, okay, well, that's just 1. That's not a big deal. They only give you 1. You're getting all excited. But it's not 1. It's 6. Because there's 6 permutations of this. And if you really want, I can write them out. Right? You can have the y-axis second and then the x-axis third. Or you can have the x-axis first and then the 180 and the y, and then the y and the 180. Or you can have the y first and then the 180 and the x, or the x and the 180. So look at that. As you can see, 6 permutations, and that is pretty good progress. Now, are there any others? Well, of course there are, because the answer choices are greater than 6. So now we have to think. The only other way of doing this is we've, I think, exhausted the x and the y's, because in the x and the y's, if you put anything else, it won't work as a third choice. And if you put just x-axis like that, then the third choice will make it different than the original position. So now what I want to do is concentrate just on the angles. If you move something 90 degrees, right? Let's just concentrate on a point. I think it's easier. It'll go to here. Another 90 degrees here. Another 90 degrees here. Another 90 degrees back to its original position. So that's a rotation of 360. If I can move, therefore, the shape 360, I will bring it back to its original position, or any multiple of 360, like 720. So let's see, can I get 360? I think so. 90, 90, and 180 should do it, right? 90, 90, and 180. That is 360. And then there's going to be three permutations of this. 90, 180, 90, or the 180, 90, 90, like that. And I think that's a rotation of 360. So that would bring it back to its original position. And any multiple of 360, so 720 is another multiple. Can I get a 720 with any combination of that? And I think so. 270, 270, and 180. 540. Yeah, that's 540 would plus 180. So it would be 270, 270, and 180. And then, of course, there's going to be three permutations of this. So 180 could go second, or 180 could go first, and then the 270s are the other two moves. And I think this is it. This is the full. This exhausts all our possibilities. So we got 6 here, 3 and 3. That's 12. Therefore, number 23, the answer is A. Let n be the least positive integer greater than 1,000. So n is greater than 1,000. For which the GCD, greatest common divisor of 63 and n plus 120 is 21, and the GCD, greatest common divisor of n plus 63 and 120 is 60. What is the sum of the digits of n? Well, the GCD of 63 and n plus 120, they're saying, is 21. So that basically means that 21 has got to be divisible into each of these. So 63 is 3 squared times 7 to the power 1. So this guy here has to be 21 times something. So 3 times 7 times, let's just say m. So n plus 120 has to be 3 times 7 times m. Whatever that m is, I don't know yet. And m has to be chosen in a way so that it doesn't change the GCD. And we'll talk a little bit more about that later. But let's just set up the question first. The next part is that guy. So very similar, GCD, this time n plus 63, and 120 is 60. So that means that 60 has to divide into both of these. And 60 is what, in terms of its prime factors, 2 times 2 times 3 times 5. And 120 is 2 to the power of 3 times 3 times 5. And therefore this guy has to be 2 times 2 times 3 times 5 times something. We'll just call it k. And k has to be selected in a way so that it does not change the GCD. And we'll talk a little bit about that later. So that means this n plus 63 has to be equal to that, which is essentially just 60k. All right. So that means n is equal to, this is 21m minus 120. And n is equal to 60k minus 63. So we can equate both of these. 21m minus 120 is equal to 60k minus 63. So that means that 21m is equal to 60k plus 57. Okay, that's great. And n is greater than 1,000. All right, and here's my n. So I'll just write n has to be greater than 1,000. Okay, so now what do I do? Well, it basically boils down to finding integer solutions for that equation. But where do I start? Okay, there's probably many infinite, well, yeah, I don't know if it's infinite, but there's many integer solutions. Well, I can start one place with this bit of information that n is greater than 1,000. So that means since n is greater than 1,000, then that's going to help me at least begin my journey for integer solutions by saying 60k minus 63 has to be greater than 1,000. Okay, so that means 60k is greater than, subtract or add 63 actually, 1063, and then divide through by 60, and then see what, just an approximation as to what, and you're going to get about 17.7. So k's got to be greater than that, right? So I don't need to worry about any values greater, less than that. So I'll make a little table, m, k, n, and then the sum of the digits of n. All right, so let's see. Hopefully I don't have to do too much here. So if k equals 18, you sub it in, and then you see what you get for m, and if it's an integer, great. The first one I get is when k is 19. When k is 19, I get 57. So I get all excited. I think, okay, great. I didn't have to do much work here. But the problem is, this doesn't work. They say, well, why? Why doesn't it work? Perfectly good integer solution to that equation. Well, here's the reason. If m is 57, what is 57? Well, 57 is 3 times 19. So this would become 3 times 7 times 57, which is 3 times 19. If that is the case, the GCD would no longer be 21. The GCD, as you can see, you can extract 2 powers of 3 there. So it would be 3 squared, because you can extract 3 squared from there as well. So the GCD would end up becoming 3 squared times 7, which is 63. So that means that's no good. So m equals 57 cannot be used. It is an integer solution to that equation, but it doesn't work for us. Okay, no problem. Keep going. And when you keep going, eventually you get to 26 for the value of k. And it goes up by 7, so some of you might have been able to figure that out, that you have to go up by 7. 19 plus 7 is 26. Okay, when k is 26, what's m? It's 77. Okay, is this valid? Is this going to be legit? Well, unfortunately, the answer is no. Why? Because if k is 26, so now we're looking over here, you'd have 2 to the power of 2 times 3 times 5 times k, which is 26, which is 2 times 13. If that is the case, the GCD wouldn't be 60. The GCD, you'd be able to extract 2 to the power of 3 from this guy, as you can clearly see there. So the GCD would end up becoming 2 to the power of 3 times 3 times 5. And as you can see, that's 120. And that is not 60. So that's no good. Okay. I think I can go up by 7. If I go up by 7, I get the next integer solution. It's nice to know that you can just go up by 7 instead of having to go 27, 28, 29. And then when I do 33, I get 97. Does this pose a problem? Well, let's see. When k is 33, I've got 2 to the power of 2 times 3 times 5 times 33, which is 3 times 11. Does it change my GCD? No. Maximum is 1, 3, so I can only take out 1, 3. I'm not affected with the 2's. No, the GCD stays 60. Okay, great. So 33. What about 97? Well, 97 is a prime number. So this becomes 3 times 7 times 97. So that definitely doesn't change the GCD. There's no 97 here. So this works. And when you have m as 97, k as 33, n, you can just sub it back into either one of those. It would be 1917. You can use that one or this one. And therefore, the sum of the digits of n would be 1 plus 9 plus 1 plus 7, and that is 18. So the answer to this question is C. Jason rolls 3 fair standard 6-sided dice. Then he looks at the rolls and chooses a subset of the dice, possibly empty, possibly all 3 dice, to re-roll. After re-rolling, he wins if and only if the sum of the numbers face up on the 3 dice is exactly 7. Jason always plays to optimize his chances of winning. What is the probability that he chooses to re-roll exactly 2 of the dice? On his initial roll, he will have 3 numbers. And we want to see how we can get a sum of 7. Well, 511 would do it, and there's going to be 3 permutations of that. I'm not going to write out all the permutations. I assume you know how to do that. You can also have 421. That gives me 6 permutations. 331, that also gives a sum of 7. 3 permutations of that. And 322, that has 3 permutations. So in total, I've got 15 ways of getting a sum of 7 when 3 dice are rolled. Now, what is the total number? Because I want to get the probability. 15 is the numerator, but what's the denominator? For each of those 3, I have 6 possible outcomes, 1 through 6. So the total would be 6 possible choices for the first, 6 possible choices for the second, and 6 choices for the third. So that's 216. So that is the denominator. In lowest terms, that's 5 over 72. So this is the probability of him winning when he just rolls 3 dice. And that's it. He doesn't go any further. All right, so now the question is asking us something very specific. It's saying, what is the probability that he chooses to re-roll exactly 2 of the dice? So I'll give you a scenario. Let's say we have an initial roll, and we rolled 3 numbers. And one of them, we'll just start with the number 1. The first dice had a 1 on it. And the other 2, we don't know, but we know that he didn't roll a 7. Okay. Then he's going to pick up this dice and roll it again. So the number of dice that he re-rolls is 2. Exactly 2. If he does, what is the sum of those dice in order to win? Well, the sum has to be 7 for all 3. We already got a 1, so the sum has to be 6. So how do you get a 6? Well, you can get a 6 in a few ways. You can get either a 5 and a 1 and a 5. You can get a 4 and a 2 and a 4, or 3 and a 3. Yeah, 3 and a 3. So as you can clearly see, there's 5 ways of winning these 5. So 5, the probability, over 36. Why 36? Because the first dice, there's 6 possible choices, 6 possible outcomes. And for the second dice there's also 6 possible outcomes. So that's why you get that 36 there. And of those 36, 5 would make him win. All right, so that's an important number. How about if you had an initial roll and you had 2 as the first number, and then he didn't get 7, but he wanted to re-roll these 2. Same thing, you need a 6, so you only get, you need a 5, because 5 plus 2 is 7. So how can you get a 5? Well, 1 and a 4, 4 and a 1, 3 and a 2, or 2 and a 3. So as you can see, there's 4 ways of the 36 possible outcomes when 2 dice are rolled. Let's just put that 2 there. How about if I have a 3? Well, this sum has to be 4 now, because 4 plus 3 is 7. And how do I get a 4? Well, either a 1 or a 3 or a 1, or a 2 and a 2. So there's, as you can see, 3 ways, these 3, out of the 36 possible ways, outcomes, when 2 dice are rolled. Okay, so here's the part of the question that I think is challenging. It took me a while to really understand this. Here's the thing. If he rolls 3 dice, so we're talking about this situation, right? And he gets a 7, he wins the game. All right, no need to do anything else. If he rolls 3 dice and he doesn't get a 7, he obviously needs to roll again. Now, if he needs to roll at least 2 dice, which is our scenario here, then he re-rolls them only if the probability of winning, which are these probabilities, is greater than this. So let me write that out. If he needs to re-roll 2 dice, this situation, to win, he re-rolls 2 dice if, and only if, the probability of winning is greater than 5 over 72. If it's not, then what he'll do is he'll just pick up the 3 dice and roll them again, because that gives him a better chance of winning. So if you continue this table, I wanted to stop and explain it. If this is a 4 and you go through the same thing, you will get a probability of 2 over 36. And if this is a 5 and you go through the same thing, you'll get a probability of just 1 over 36. Now, which one of these probabilities is greater than 5 over 72? It has to be greater than 5 over 72. Otherwise, it doesn't make any sense for him to re-roll 2 dice. He can just re-roll 3 dice, because 5 over 72 would have been the better probability. Well, I'll tell you. What we can do is let's put them over the same denominator. It makes it easier to compare. This is 10 over 72. This is 8 over 72. This is 6 over 72. This is 4 over 72. And this is 2 over 72. Which one of those is greater than 5 over 72? Well, obviously, these ones. These scenarios. This is not, and this is not. So let's explain again. If he needs to re-roll 2 dice, he re-rolls 2 dice if and only if the probability of winning is greater than 5 over 72, which is this guy, and this guy. For here, he will not do that. He will re-roll 3 dice, because if he re-rolls 3 dice, the chance of winning is 5 over 72. That's a better probability than if he does this, which is only 4 over 72. He obviously wants to optimize his chances of winning. All right, so I think I've beaten that to death. Now let's move on. So we have to just look at this, this, and this. Okay, so if he has 1 as the first number, then he says, okay, I've got 1 as my first number. I want to win. How do I win? 1 as my first number. Now he's got to think, what do I do here? Do I pick up the 2 dice and roll again? Well, it seems like the right thing to do, but he has to think about the second number. The second number is going to really make him decide. Let's say the second number is 2. Well, now that third number has to be very specific. It has to be a 4 in order for him to win. And he, therefore, has to understand that this third number, if it's not a 4, so not 4, he obviously has to roll again. So now he's got a choice. What do I do? Do I pick up all three and roll again in order to win? Well, if he does, there's a 5 over 72 chance right here. Do I pick up only two and roll again? Well, we just calculated there's a 10 over 72 chance. Do I just pick up one and roll again? I just pick that up and roll again, and hopefully it'll be a 4. Well, 1 over 6 chance of getting a 4, and if you put that over 72, get a common denominator is 12 over 72. So of these, which is the highest? He wants to maximize his probability of winning. The highest of these is obviously this guy. So he's just going to pick up this and roll again. He's not going to pick up 2. And similarly, the same story is if you have a 1 and a 3, and then a not 4, a 1 and a 4, a 1 and a 5, you will have the exact same story. He will just pick up the third one and roll again. The only time he's going to pick up 2 is if you have 1 and then a 6 and a not 4. But that not 4 also cannot be a 1, because then you just have the same scenario. So it has to be a 1, 1, and a 6. Any other scenario would actually be very similar to this. And I don't want to keep drilling this home, but for example, if I had a 1 and a 6 and then a 1, well, that's very similar to this right here. It's just one different. All I have to do is pick this up and roll again. So we want a scenario where he absolutely must pick up 2 in order to win, and that is going to happen in that scenario. 166, he has to pick up those 2 6s and roll again. And there's 3 permutations of that. 166, 616, and 661. All right, so hopefully that makes sense. Now let's move on to what other scenarios we have. The other scenario is if you have 2 as the first number, which is our next guy right here. 2 is our first number. And then, again, I'm not going to beat this home like I did with the first one, but I'll just give you the scenarios. The next 2 numbers, it has to be either a 5 over a 6 or a 5 over a 6. So the possible choices are 255, 266, or 256. There's 3 permutations here, 3 permutations here, and 6. So this gives me 12. So 12 in total. And then finally, we have this guy, 3. That has a probability of 6 over 72. But let me just compare the probabilities for this before I jump ahead. The probability of him picking up 2 and winning is 8 over 72, right? If he were to pick up all 3 and roll again, the probability of him winning is 5 over 72. And if he picks up just 1 and rolls again, let's say he picks up that 1, he will definitely not win because 2 plus 5 is already 7. So if he picks up 1 and rolls again, he's always going to get a sum of more than 7, so 0. So obviously of those 3 numbers, the highest is 8 over 72. So I just wanted to justify how the picking up 2 and rolling again is going to optimize his chances of winning. And now we have just one final scenario, and that is this guy. That's when you have a 3. And again, I'm not going to go through all the choices. I'm just going to list the ones that are correct. The first number is fixed as 3. The next 2 can be either 456 or 456. And that has the following permutations: either 344, 355, 366, or 345, 346, or 356. And there's 3 permutations here, 3 here, 3 here, 6, 6, and 6. So that is 18 plus 9, 27. And again, let's just review the probabilities. If he picks up 2 and rolls again, the probability of him winning is 6 over 72. If he picks up all 3 and rolls again, the probability of him winning is 5 over 72. If he picks up just 1 and rolls again, the probability of him winning is 0, because 3 and any of these numbers already adds up to more than 7. So if he picked up the 3rd and rolled again, he's never going to get a sum of 7 for all 3. And obviously of these, the highest probability and therefore optimizing his chances of winning is the 6 over 72, which is this scenario, which involves picking up and re-rolling 2 dice. All right, so now we're almost done. We have to add up these values, the 3, the 12, and this 27. So 3 plus 12 plus 27. And remember, it's a probability. The denominator is all the possible choices. And we had previously calculated that as 216. So that is what? 42 over 216. And let's see. If you divide top and bottom by 6, it becomes 7 over 36. And 7 over 36 is A for number 25.